This is Advanced Algebra, Lesson 8.4, Radical Notation for Nth Roots. In the last chapter, we looked at the positive nth root of a positive number x that was written as x to the power of 1 over n. In this lesson, we're going to explore another notation for looking at roots. So the definition of the nth root of x when x is greater than or equal to 0 is when x is a non-negative and n is an integer greater than or equal to 2, then the nth root of x is equal to x to the 1 over n power. Therefore, 32 to the 1/5 power is the same as the fifth root of 32, which is equal to 2. So the positive real fifth root of 32. So basically, what we studied all in Chapter 7 when we looked at roots is applying here as well. The nth root of x can be used to calculate what's called a geometric mean. You studied arithmetic mean in earlier chapters and in other grades, and it's often been known as an average, where you add your set of values together and you divide by however many values you have in your sample, and that would find an average value for your sample. We use geometric mean when we have values that are kind of far apart from each other. As you can see here, I have a sample where I have 8 different populations that I want to find an average for, or a geometric mean. And so you'll see that I have one population that's at 47, and I've got another one all the way at 45,312. So using a geometric mean is going to give me a better sampling or better value that represents this data than if I were to do an arithmetic mean. So what we do for a geometric mean is we take all of our values in the set and we multiply them together. And then I take the 8th root of that, or I take the root of however many I have. In this case, I have 8 in my sample, so I'm going to take the 8th root. If I had 10 in my sample, I would take the 10th root. So if I take the 8th root of 47 times 68 times 159 and so on, I get a value of 1,656. So that represents the geometric mean for my population sample. In your reading, there's a heading titled, "Which nth root does the nth root of x represent?" So the symbol, the nth root of x, like x to the 1 over n, does not represent all nth roots of x. When x is positive and n is even, x has 2 real nth roots, but only the positive real root is denoted by the nth root of x. So if you look at 3, -3, 3i, and -3i, these are all fourth roots of 81. But if we just evaluate the fourth root of 81, or 81 to the 1/4, denoted this way, we know that we only have an answer of 3. So what I'd like you to do is we're going to explore this on our CAS a little bit. The first time I want to do it in your real number mode. So I want you to evaluate the fourth root of 2,401 on your calculator. And when you do that, you should get an answer that looks like this. So what that means is the fourth root of 2,401 is equal to 2,401 to the 1/4 power. We know that represents the positive real number whose fourth power is 2,401. 2,401 to the 1/4 power is equal to 7, because 7 to the 4th is equal to 2,401. So the fourth root of 2,401 is 7. But now I want you to set your calculator to complex number mode, and I want to find all the fourth roots of 2,401. So we're going to solve the equation x to the 4th equals 2,401 in complex number mode. The solutions are 7, -7, 7i, and -7i. These solutions are all the fourth roots of 2,401. For this next part, I'd like to actually look at this section in your book that's from page 539. It's titled Radicals for Roots of Powers. Because radicals are powers, all properties of powers listed in Chapter 7 apply to radicals. In particular, because the nth root of x is equal to x to the power of 1 over n for all values of x greater than 0. The mth powers of these numbers are equal. So that is, the nth root of x to the m power is the same as x to the 1 over n raised to the m power, which can be simply written as x to the power of m over n. Now if I replace x by x to the power of m in the definition of the nth root of x, the result is the nth root of x to the power of m, which is equal to x to the power of m to the 1/nth power, which is also equal to x to the m over n. Thus, there are two radical expressions equal to x to the power of m over n. So that's where our root of a power theorem comes into play. So for all positive integers, m greater than or equal to 2 and n greater than or equal to 2, we can write it different ways. The nth root of x to the power of m is the same as treating it as a root raised to the power of m, or we can treat it as a fractional exponent here, assuming that x is still greater than or equal to 0. So let's take a look at this little quiz yourself. Supposing that x is greater than or equal to 0, use the root of a power theorem to write the 6th root of x to the 18th power in two different ways. So if we look at that, the 6th root of x to the 18th could be written then as the 6th root of x raised to the power of 18, or we could write it as x to the power of 18 over 6. And I hope you all see that that could be x simply to the power of 3. So at the bottom of your note page now, there should be one more example to try. We want to rewrite the second root of the second root of the second root of the second root of 10 using rational exponents. And then we're wondering, is this expression an nth root of 10? So let's look at this. If I were going to write this in fractional form, I would write that as the 10 to the 1/2 power to the 1/2 power to the 1/2 to the 1/2 again. And that would be the same as 10 to the power of 1/16. And now the 16th root of 10 is equal to 10 to the 1/16th power, because the 10th root of 1/16 raised to the 16th power is equal to 10 to the 1st, which is equal to 10. We will continue our study of radical notation for nth roots in class. This concludes lesson 8-4.